In the name of God, the most gracious, the most merciful, peace be upon you and God's blessing. In this video, we will be talking about the elastic section modulus S sub x, the plastic section modulus Z sub x, and the shape factor. Also, what are the steps to get S sub x and Z sub x for any given shape. First, we start with the elastic section modulus called S sub x. When we have a rectangular section B by H under a moment, the stress at the upper fiber has reached to yield. The stress at the lower fiber has reached yield. The beam will deflect like this shape due to bending moment. The upper fiber will have compression stress, while the lower fiber will have tension stress. At yielding, both compression stress and tensile stress will be equal to F sub y, where F sub y is the yield stress. The stress at a yielding moment for a rectangular section of dimension B by H was estimated as F equal to M sub y by y over Ix, where M sub y is the yielding moment about the x-axis, y is the distance from the elastic neutral axis to any fiber. The maximum F value will be reached when y equals h over 2, where h is the overall height of the section and will be equal to F sub y. Ix is the moment of inertia about the x-axis. The moment of inertia Ix value will be the parallel by the perpendicular raised to the power of 3 divided by 12, or b by h cubed divided by 12. The yield stress F sub y equals m sub y by h over 2 divided by bh cubed over 12. Adjusting the terms and letting S sub x equal Ix over h over 2, we will find that F sub y equals m sub y divided by bd squared over 6. The term bh squared divided by 6 is called the section modulus S sub x, and we can later estimate the elastic section modulus S sub x value for various shapes, whether I-beam or rectangles, triangles, WG shape, or hollow steel section, HSS sections, etc. We will move to the next slide. The second subject, by God's will, is the plastic section modulus Z sub x, as we have explained in the last video. If the load acting on the beam is increased, more than the load creates the first yield in the upper fiber, until the stress F sub y propagates from the upper fiber to the lower one, and the section becomes fully yielded, and thus we get our plastic neutral axis. The stress profile has changed from a triangle to trapezium shape. In the end, it will become a rectangular shape as shown in the sketch. If we consider the symmetry, the area above the plastic neutral axis will be equal to half of the area, or A over 2, where A is the total area of the whole section. The compression force will act on the upper section. This force at plastic stage C sub B equals to the F sub y by the area of a rectangle PH over 2, or F sub y multiplied by area of a rectangle BH over 2. There will be a tension force T sub B equal to the compression force C sub B for the lower portion below the plastic neutral axis. C sub B equals to T sub B equals F sub y multiplied by BH over 2. Both forces will act on the CGs, or the center of gravities, at h over 4 above and below the neutral axis. The term YCT is the distance between the tension and compression forces, which will be equal to h over 4 plus h over 4 equals h over 2. Let us write the following information in an equation where C sub b equals to T sub b equals to F sub y by A over 2, YCT equals H over 2, the plastic moment M sub b will be equal to F sub y by A over 2 by H over 2. A new term Z sub x, or the plastic section modulus, will appear. The value of Z sub x equals to A over 2 by H over 2 equals B multiplied by H divided by 2 by H over 2 equals BH squared over 4, or Z sub x equals to A over 2 multiplied by 2 y bar. This is the 1 y bar distance measured from the CG of the upper area to the plastic neutral X. This is y2 by y bar equals to 2h over 4 equal to h over 2. In the case of a rectangle, the plastic section modulus Z sub x equals to b multiplied by h divided by 4. What is the shape factor? The shape factor is the ratio Z of sub x divided by S sub x, or the plastic section modulus divided by the elastic section modulus. The value of the shape factor of a rectangular shape equals 1.5. We will move to the next slide. Consider a rectangle of dimension b by d. We will derive an expression for the CG distance from the lower base of the rectangle. In step 1, let a datum line pass by the lower base. Consider another x located at a distance of kd from the lower datum line. This x will have a distance from the upper fiber equals d minus kd. Step 2, estimate the area A sub 1. Let A sub 1 be the area enclosed by the upper datum axis and the top side of the rectangle. We can estimate the area A sub 1 as equal to B multiplied by D minus KD equals BD by 1 minus K. If we let Y1 is the distance from the CG of the upper area A sub 1 to the lower datum, we can estimate Y1 value as equal to KD plus 0.5 multiplied by D minus KD equals D over 2 by open bracket K plus 1. Then the first moment of area, or A sub 1 by Y1, equals BD multiplied by 1 minus K by KD by D over 2 by K plus 1, can be rewritten as BD squared over 2 multiplied by 1 minus K squared. The third step is to estimate the second area, or A sub 2. It will be equal to B by KD. If we let Y sub 2 be the distance from the CG of the lower area A sub 2 to the lower datum, we can estimate Y sub 2 value as equal to KD divided by 2. The sum of moment of areas is equal to BD squared divided by the total area, which is equal to BD. We can get Y bar, or the distance of the CG of the rectangle area from the bottom datum, as equal to G over 2. If we move to the next slide, due to symmetry, Y bar, which we have estimated is the distance from the bottom to the elastic neutral axis, will divide the rectangle into two equal parts. We can get the S sub x as equal to Ix divided by Y max, where Ix equals to BD squared over 12 and Y max equal to G over 2. The elastic section modulus S sub x for a rectangle will be equal to BD squared divided by 6. The elastic neutral axis will divide the shape into two equal parts due to symmetry for shapes like W sections, M sections, and S shapes. For the C shape, it has a symmetric axis which is XX, so the elastic neutral axis will pass by the x-axis. In the next slide, three shapes are doubly symmetrical about both x and y axes. The elastic neutral axis pass by the x-axis. In the next slide, there are two examples of situations where the elastic neutral axis will not divide the shape equally. These shapes are WT shape and unequal angle. What will be the steps to find the neutral axis if we have an unsymmetrical shape? We will indicate this in the next slide. For the shapes where the elastic neutral axis will not pass by the middle, we will follow the following steps. Create datum line, for instance, passing by the bottom of the shape. Use any arbitrary axis. This axis will divide area into A sub 1 and A sub 2. Estimate A sub 1 and A sub 2 and find the total area that is equal to A. Estimate the distances Y sub 1, Y sub 2, or the CG distances for area A sub 1 and the CG for the second area A sub 2. Estimate the elastic neutral axis distance from the bottom datum by dividing the sum of A multiplied by Y over the area. The elastic neutral axis can be located. Estimate the Ix value for the shape above the elastic neutral axis. To get the elastic section modulus, divide Ix over Y max. Y max is the maximum value of the Y top and Y bottom. For the plastic section modulus Z sub x, create a datum line, for instance passing by the bottom of the shape. Use any arbitrary axis. This axis will divide area A into two equal areas, each equal to A over 2. Estimate the distances Y1, Y2, or the CG distance for area A1 and the CG of the second area A2 about the external datum. Estimate the plastic neutral axis distance from the bottom datum by dividing the moment of area over the area, and get the expression of Y bar equals 1/2 multiplied by Y1 plus Y2, where Y bar is the plastic neutral axis distance from the external datum. Estimate Y1 bar and Y2 bar about the plastic neutral axis. To estimate the plastic section modulus Z sub x, use the expression of Z sub x equals A over 2 multiplied by Y1 bar plus Y2 bar. For the plastic section modulus Z of x of a rectangular shape, in step 1, let a datum line pass by the lower base. Consider another axis located at a distance of KD from the lower datum line. This axis will have a distance from the upper fiber equals to D minus KD. Step 2, estimate the area A1. Let A1 be the area enclosed by the upper datum axis and the top side of the rectangle. We can estimate A sub 1 as equal to B multiplied by D minus KD equals BD multiplied by 1 minus K. The third step is to estimate the second area, or A sub 2. It will be equal to B multiplied by KD. Equate A sub 1 and A sub 2. BD multiplied by 1 minus K equals B multiplied by KD. We can get an expression for K as equal to BD divided by 2BD equals 1 over 2. Thus, the plastic neutral axis will be located at distance KD distance, which is D over 2. Let Y1 CG is the distance between the plastic neutral axis and CG of area A1. It will be equal to D over 4. Similarly, Y2 CG equals D over 4. Z of x can be equal to BD squared over 4. Thanks a lot, and peace be upon you all.